already had, and this happens every year in CAT. I want out of here after the first one or two tests. First of all, they make it like it's like you'd have a better chance of breaking into the Pentagon than getting out of a class right away if you have not gone to Compass, gone to tutoring, gave it the old college try. And this happens every year. Every year in CAT, after the first test or two, I get that happening. I'll tell you one great story. I don't know if I have time for this. I don't care. This is important now. Remember her name, Miriam. I know her last name too, but Miriam B. Hey, Miriam, if you're still out there, we're talking about you. I gave the old "Are you in the right class?" speech, which I don't do anymore. And are you ready? And if you got a C in Algebra 2, which is what we used to have, you're gonna have a really tough time getting a C in here. Now Math 3 regular has changed the whole thing. It's just that class. I don't think it's strong enough to get you truly prepared for the beginning of CAT, and you got to change what you're doing. All right, if you truly want to go to college. And usually in college, this is the minimal mathematical requirement, no matter what your what's the thing do that you do the rest of your major, right? Sometimes they have hard times with words. So here's the sad thing that happens: students want to quit, or you may know seniors that didn't take a math this year. They go to JJC, they take an entrance exam, and then they get placed in high school level math courses because they're not going through the process this year. All right. And it happens all the time. It happens way more than it should because people think, oh, I'm just going to take a year off of math. I hated it anyway. And then your prerequisite math is not up to snuff. So you're paying college money for a high school course, the course that you're taking or looking at right now. So that's another reason it's not a negative thing to say it's like trying to break into Fort Knox to get out of a class. Are you truly approaching it the right way? Back to that Miriam. I asked her, "Are you in the right class?" She had a D as in Danny the year before in Algebra 2. So she came the next day with a drop form. I'm like, all right, just hold on. We can drop in maybe 2 weeks. Let's give it a try. Long story short, she ended up with a B as in boy in the class that was higher than the one that she had before because she, I think, listened to the things that I said, how the approach should be, and did things like in that manner. So this happens every year. Not picking on anyone individually. Oh, my pen. Can you go get my pen? Otherwise, this thing will strangle me and I'll die during the notes. Thank you. Sorry, I left it over there. Oh, did you make the video? Maybe you did. You can sue me now. I didn't give you the rights to put me in the video. All right, so now this is my sad attempt. Pay attention over there. That group kills me. All right. Now, I synthesize this. Hold on, it's not working. Let's see. Okay, I know what I got to do. All right. I synthesize this, but does it look great? Maybe not. And I wanted to start with domain and range. I want to number these so my numbers coincide with our synthesizing the notes tomorrow. All right. So that's what I tried to do. So I'm in the domain range thing, but to do that, I got to talk about asymptotes. And I didn't want to stop and have you write all this down. But it does happen when a graph appears to flatten out to the right or left. And we should recognize that when we look at the graphing calculator. So, all right, first of all, vertical asymptotes, that's when where x is undefined. And go ahead and squeeze this little graph in here, y equals 1 over x. We're going to talk about this for sure tomorrow and Monday. You're going to have to know how to graph this. Input, say it. When I input 0, I get undefined. What ends up happening is, maybe I'll change colors, and I talked about this yesterday a little bit, and you saw asymptotes last year. I know you did. I know it. All right. It actually does create, it doesn't create a vertical asymptote, but here's the behavior of the graph. And I can prove this. I can prove this by input output. The graph, when you go ahead and put it on the graphing calculator, looks like this. Okay, listen. Input, I input 1. When I input 1, I get 1 over 1, which is 1. That's that point right there. See it? See how I put that point there? Now listen. When I plug in 2, 3, 4, that's for later. I'm not doing that right now. When I plug in 1/10, so as I get closer to 0 from the left side, as I plug in half, 1/4, 1/10, What happens to the y values? Well, we got to know fractions. What's 1 divided by 1/10? The answer is 10. When you divide by 1/10, it flips in mind. I see some faces like, what? That's grade school. You got to know how to divide by a fraction by flipping. All right. Fractions are going to crush us. So as I go closer and closer to 0 from the right, the y's start taking off. That's why that arrow is the way it is. Let's go to the other side. I plug in -1 for x. I get -1 comma -1. Now the graph is below the x-axis. And then when I get closer to 0 from the left side, when I plug in -1/10, then I get -10 as my output value. 1 divided by -1/10. So as I get closer, -100th, when I plug in -1/100, that becomes -100. So that's why that arrow goes forever down. So when we see this behavior, humans create this asymptote so that they understand there's that boundary there. Right? The graph is doing that because of my input outputs. So that's a vertical asymptote of x equals 0. Now, how do horizontal asymptotes happen? Now, this is specifically to fractions, which are called rational functions, which we are really going to graph in chapter 2. So you're going to see this again in chapter 2. When the higher power is on the bottom, then automatically you have a horizontal asymptote y equals 0. That is right here. I asked this of last hour, nobody got it right. What's the degree of the numerator? What is the power on x? 3, 2, 1, go. Oh, there is no x. You know what x to the 0 power is? What's anything to the 0 power? 0. Oh, no. It's 1. 1. So, what's the degree of the numerator? 3, 2, 1, go. 0. What's the degree of the denominator? 1. The lower, the bottom has a higher degree. Automatically, the horizontal asymptote is y equals 0. Oh, I see that. And now I can do input output again. What the end behavior is, which I end the notes with, but I don't know if I'm going to make it, especially my little speech earlier. When I plug in big numbers, when I plug in 5, 1/5. When I plug in 10, 1/10. When I plug in 20, 1/20th. Who's bigger, 1/5, 1/10, or 1/20th? 1/5. Okay? She never answers any of my questions. All right. So that's what I'm proving. The point that as I plug in big numbers, your y value is approaching a smaller and smaller number, which is 0. This is called end behavior. So we're annoyed by like trying to calculate that. So we draw the horizontal asymptote. All right. Now, for the next part, when the powers are the same, then the asymptote appears at the coefficients. Write this down. Y equals. Let me zoom in on this. And again, you have really small space for this. Let's say like 3x squared over 2x squared. And I'm only doing horizontals. I don't care about verticals right now. I'm just throwing something down. Now, here's what happens. Again, a horizontal asymptote is end behavior. What happens when I plug in big numbers? When I plug in big numbers, these squareds actually cancel each other out. So say I plugged in, let's try to do like 1,000. When I plug in 1,000 squared is 1,000,000. Times 2, 2,000,000. When I plug in 1,000, I think I get 1,000,000. I'm doing that right? 3 zeros squared is 6 zeros, so 1,000,000. Times 2, 2,000,000. Plus 1 is irrelevant. What's 3,000,000 over 2,000,000 reduced to? 3 over 2. So your horizontal asymptote is actually y equals 3 over 2. So you may have heard and talked about horizontal asymptotes before. You may not have been told it as an input-output when you plug in big numbers, what actually happens. Because that's what's true. The higher powers dominate and everything else is irrelevant. That plus 1 is irrelevant. Even if I put plus 1x, this would still be irrelevant when I plug in 1,000,000. I'm sorry, 1,000. This becomes irrelevant. The high powers dominate, and therefore it approaches 3/2. When the power on top is higher, none. So when you have 3x to the 4th over 2x squared plus 4x minus 1. Doesn't matter. The higher powers on top, there is no horizontal asymptote. Now, again, this is specific to what's called rational functions, fractional functions with variables in it. Okay, so now I have these examples here, which you see, you don't have to write them. That's another speed factor. Good FOILers are 3, 2, 1, go. Good factors. Okay, good. Most people say it. Some haven't said anything all year long. What multiplies to -2 and adds to -1? 3, 2, 1, go. -2 and 1. X minus 2, x plus 1. Because even though this is chapter 2, in chapter 1 we got to talk about domain and range. So therefore we got to talk about vertical and horizontal asymptotes. So the vertical asymptotes, you cannot plug in 2 for x. You will get a 0 in the denominator. Therefore, that's a vertical interruption. You cannot plug in -1 for x. Therefore, it's a vertical interruption. Therefore, when I look at the graph, we'll see the domain is affected. So the domain, and actually this is something you should have done and you should have looked at your calculator and analyzed this and known about asymptotes to say the domain in this fashion. All right, but let's graph it first, and then we'll talk about the range. So let's go ahead and clear. Move my fat head over here, and then do this, and then do that, and then type it. And then I'm going to show you something. Actually, I just blew somebody's mind blown during tutoring today. Didn't know that this button existed, and I've already showed you. And if you are the same person, I had another kid that was in my class last year. He goes, oh, yeah, I didn't learn that till May. I go, dude, I showed you that in August, September, October, November. What were you doing? All right. And I'm showing you this right now, and you guys make me sad that don't follow second y equals. Now, not everyone has this, but I hit the second y equals, and then that menu came up. That's a fraction. Press enter, and now I can write this exactly as this looks in fractional format. All right. So just blew that guy's mind today. I never knew that button existed. All right. X squared. So anyway, so what happens maybe when we don't bring our calculator or don't type along with me? These are the things that just don't work in my class, right? And that's why I do have problems with certain actions. But anyway, I just keep complaining until everyone gets on board. All right, let's go back here and hit, I'm in the way. You know what? You're gone, Mr. Samuelis. All right, graph. Okay, there we go. So I see the vertical interruption here, all right, at 1, and 2. Okay, so the domain is definitely -infinity to infinity, except for -1 and 2. And this is where interval notation is not the best. I mean, it gets kind of wordy and difficult to write. I mean, it's just lengthy. All right, but then when I look at this graph again, I notice something. Look at the ends. We should at least be able to look at how these end. All right, and then I'm going to go back to this. What is the horizontal asymptote then for this? Well, let me ask you this. What's the degree of the numerator? Everyone should be able to get this right. 3, 2, 1, go. 1. It's actually 1. X to the first. Everyone should get this right. What's the degree of the denominator? 3, 2, 1, go. 2. The degree of the denominator is bigger. So it automatically goes to y equals 0. Okay, I could see that. I can draw y equals 0. I can go into y2 and put y equals 0. I can't draw vertical lines. See that red line? Look at the ends. It looks like it's approaching that red line, right? So it does exist, and that is true. But what's the range? Look at the middle. Oh, no. Look at the middle. What's the range? -infinity to +infinity. Just because we do have that horizontal asymptote, unfortunately, that middle part covered and went through it. So the range is still all real numbers, even though there is an end behavior asymptote. Notice what I said, end behavior. Now think about the middle. So horizontal lines could be crossed, horizontal asymptotes, I mean. All right, next one. Speed this up a little bit, afraid of time. My little speech at the beginning. Clear, and then I don't want this anymore. Clear, and then fraction. Second y equals. I didn't know I had that button. Ah! Okay. 2x squared. Yes? Those can affect domain and range, yes. But they're that's why we're kind of covering them synonymously. What's that? This first one? I put them. What happened? Ah, they're right here. I wrote them. Yeah, those are the vertical and horizontal asymptotes. Yeah. All right. Okay. All right. Okay. Graph. But wait, I shouldn't have done that. Don't look. Okay. First of all, vertical asymptotes. Okay, how does this factor? This is a say it difference of two squares. Don't switch them. What's the perfect square of 4? 2. What's perfect square of x squared? X. Plus minus minus plus. I couldn't care less which one you write first. Know what to tell you. Got to be a good factorer. Sammy Samuelis. I just worked with her factoring yesterday. Nobody cares, Mr. Samuelis. X equals -2 is the vertical asymptote. That's for this one. X equals 2. What's the horizontal asymptote? First of all, what's the degree of the numerator? Degree of the numerator is what? 3, 2, 1, go. 2. Now we're getting that. Maybe I should talk degree before, but it's the power. What's the degree of the denominator? 2. They're equal. What is the horizontal asymptote? Y equals, hold on. Y equals 3, 2, 1, go. Oh. 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 2 over -1, which is what? -2. That's what we mean about the coefficient. The coefficient in front of the highest degrees. So it's an x squared over an x squared. Everything else is irrelevant. 2 over -1. Maybe you should write 2 over -1 so you know where that came from and highlight that. Because look at the graph. It appears, okay, I can do it. It appears that they are approaching a boundary of -2. Notice that I said that boundary, but that doesn't apply to this one. Forget it. We're going to do boundedness later. See how that graph appears to be approaching that red line? Okay. Now we got a big problem. Range. Okay. First of all, is this function 1-to-1? Yes or no? 3, 2, 1, go. No, because how many times does it cross this horizontal line? Twice. But notice that these y values are covered all the way up to here. Then there's a skip, and then all of these y's, and that's not 1-to-1 either, are covered. So what I need is that low point. Second calculates. And then what was that called? What do you think I'm going to hit here? I said at that low point, so what am I going to hit here? Minimum. I'm actually going to show you this later. I am max minimums. So this is kind of like, something for the future. So notice it says left bound. I need to go left. Press enter. I got to go right. I got to go right of that low point. It's left and right arrows. And then notice the two arrows are pointing at each other. I get a fancy calculator with the lines there too. It'll give me the lowest value in between those, and that point is in between those. Guess? Press enter. Okay, I'm glad this happened. This has got to be known for the rest of the year. Going to be annoying. You're annoying every day, Mr. Samuelis. 1.06 times 10 to the -6. That's first what that means. Here comes the annoyance. That means this is 0.0000106, which is essentially what number? 0. This is even more ridiculous, and I think these two answers are different than what I had last hour. This is, you ready to be annoyed? .0.0000000000056. What is that essentially? Zero. This is a calculator conundrum. This is a calculator computer malfunction. I guarantee, as a Federmact, I can go here and tell you that 0, 0 is a point. Plug in 0 for x, you get 0 on the top over 4. 4 minus 0 is 4. What's 0 over 4? Input output 0, 0 is a point. This is a calculator conundrum. Anytime you see these -5, -6, -13, it's 0, okay, for scientific notation. So anyway, the range is affected. First of all, the domain, and domain and range are the toughest things that we have to talk about. So -infinity to -2, union at -2 to 2, union that with 2 to infinity. That coincides with these. These are all together. The horizontal asymptote did affect the range a little bit, but then there was more. There was that little gap in there that we had to account for. So the range was -infinity to -2, union that. Now, didn't I just input output 0 and got 0, correct? So what do I put on 0, a parenthesis or a bracket for the range? It exists as a range value. -2 doesn't, because the idea of a horizontal asymptote, it's approached. Sometimes a horizontal asymptote is crossed, though. I think in this case, we're fine with that. Okay? All right, we'll speed this up. Input, say it. Output. Okay, I think I already asked this. I asked what's x to the 0 power. And now what's the right answer? 3, 2, 1, go. 1. No, not anyone said it again. All right, short-term memory loss. So what's 5 to the 0 power? 3, 2, 1, go. 0, 1. So you do have that graph there. Just mark it. What happens when you plug in 1? By the way, input, output. What happens when I plug in 1? What do I get as an output value? 3, 2, 1, go. Okay, you do know that's 5 raised to the x power, right? All right, and then 5 to the second is what? 3, 2, 1, go. And then we can see this behavior. We're starting to get ridiculously large as we get powers of 5. But then let's go the other way. Oh, and if you say -5, just get out of my classroom. You can go sit out in the weeds the rest of the year, even in the snow. So the answer is not -5. What's 5 to the -1st power? 3, 2, 1, go. No, not 0. No, we're just making up numbers. 1/5. Look at everyone. Look, woo, everyone looked at him like everyone should know the negative exponent rule. It's the flipping rule. So then what's 5 to the -2? 1 over 25. And then what's happening as I plug in bigger negatives, which is a bad way to say it? The numbers get infinitely smaller. But will they ever get to 0? So we get annoyed as humans, 1, 5, and then these small numbers. We get annoyed doing this, so we draw an asymptote. We draw a boundary. We say we know that this will not be able to get any lower than 0. So an asymptote isn't just there. We draw it, so we are telling the looker of this graph that graph cannot get any lower than 0. So we draw the asymptotes. So there is a horizontal asymptote at y equals 0 just by default. There is no vertical asymptote. So what is the domain? All reals. Not just because of an asymptote, it's just because you can take 5 to any power. And then what is the range? Well, we got a big missing chunk down on the bottom. So the range is 0, bracket or parenthesis. 3, 2, 1, go. It's parenthesis because it can never make it to 0. And then above, 0 and above. Okay, you're going to be graphing this function by hand on Monday. All right, and then does this have any asymptotes? Says nothing to do with it, but I am going to do domain and range. I'll do domain and range. Input, say it. What am I going to put in there? What's the first point I'm going to put in? Don't say 0. 4 is the right answer. I mean, I could put any, but 4 is really the starting point of this graph. 4 minus 4 is 0. Square root of 0 is 0. Plus 5 is 5. So I got 4 comma 5. I'll start by graphing that when I get to the graph. Can I plug in 5, 6, 7, 8, 3? Yes. What's 4 minus 3? Square root of 1. 1 plus 5. 6. All right. And then what's the next one I should plug in to make my life easy? 3, 2, 1, go. 0, not 1, 0. What's 4 minus 0? 4. Square root of 4 is what? 2 plus 5. 7. Okay, so then wrong. That's not. I wanted it more over here. I don't want it in the way of my. Okay, I'll put it here. Okay, so 1, 2, 1, 2, 3, 4, comma 5, and then 3, comma 6, and then 0, comma 7. So it is that square root look, but it's going in the other direction. That's because you'll find out on Monday, maybe, about transformations. That's a y-axis reflection. The ones we had yesterday went like this. Now it's going in the other direction. But whatever. What's the domain? Well, the domain is these x's all the way up to the ending of 4. So when you look at this picture, we got to be able to read that it's negative infinity to 4. What kind of thing do I have on 4? Bracket or parenthesis? 3, 2, 1, go. Bracket, it's in there. It's on the chart. And then the range actually starts at 5 and goes up forever. This does rise forever. So the range is 5 with a bracket. You got the first one, so you should be able to get the second one to infinity. So no asymptotes. I just wanted to talk more about domain and range of another special function. Okay. Next, number 4, continuity. Put number 4 by this, so it coincides with our notes tomorrow, our quick cheat sheet notes, 1 page. And then this is simple, okay? The first one, this is what it means to be continuous. When I draw a graph and I never have to pick up my pen, it's continuous. Most things are, okay? Even the last graph, even though it has a starting point, once you start it, it's continuous, so it's considered continuous. But then you could have things that have what's called a hole in it. I don't know if you could see that, but maybe highlight that. This is just one case where the hole could be defined by another y value, maybe like a piecewise function, but just they're both the same. This is called, if you can't read this, right, removable right by it. Reason they describe this as removable as it can, if you put a patch there, then it would be continuous, but it's not. The next one, I mean, this is easy. I used to play a game called like Doodle Jumper, so I don't know what it was called. And there was a little guy running, or girl, or whatever. And then how would I get from here to here? Draw the guy in your notes. How would I get from here to here? You'd have to what? Jump. That's why it's called a jump discontinuity. So simple. Then the last one, when you have, hey, we just had that. When you have an asymptote that interrupts, this is called an infinite discontinuity. I didn't want to spend a lot of time on discontinuities, but I will jump to the calculator, and that's what this section's about. And no, I won't. I'm going to cheat and put the graph right there. But look, we got a problem. First of all, and you have this in front of you, so it doesn't matter that I'm zoning in and out here. What can I factor out of that top? X. That's called GCF factoring. What's left over? X. Oh, yeah, you're right. X squared what? Plus 1. But wait a minute. This is over X? Am I allowed to cancel these X's now? Yes, but here's the problem. That was in the original. When I plug in 0 for X, you should understand I do get 0 over 0. What do you think 0 over 0 is? 0, or some people might say 1, and neither answer is correct because it's still what? Undefined. Type it on your calculator. Type 0 divided by 0. The calculator never lies. Don't trust me. It says 0 divide by error, right? So the point of this is this. This is not a vertical asymptote. This is where a hole actually happens in a graph. This is why you see a parabola, because you really see this graph. You really see x squared plus 1. But honestly, there's a hole right here that you cannot see unless you looked at the charts, which I cut off right here. When you look at the chart, 0 comma, it says 0 comma fumble error. Okay, so that's a problem. So the point is, what kind of discontinuity is this? I don't have time for this. Removable. That wasn't even a word choice. Come on now. Removable. And then you should know instantaneously what kind of discontinuity this is. By the way, what's the horizontal asymptote? 3, 2, 1, go. Y equals. Okay, and it is right here. Y equals 1, and you can see that behavior. But I don't care about that for this. What's the vertical asymptote? Nobody answered. Oh, hey, no. 2, there we go. And then it shows right there. So what kind of discontinuity is this? I have no time for this. Yeah, infinite. When you have to answer those questions. Let's move on. That's too much time on that. Isn't this fun? All right, next, increasing, decreasing, and constant. Listen! This is the most important thing that I wrote here. These words describe the range as you plug in the domain from left to right. So I'm going to show you just in one of these examples how you answer it. And you must stick with me. I know it's a lot of stuff. Okay? So you probably can't see this because the graph is real small and the highlighting's there and it doesn't show up well. So if you want to like scratch a graph real quick, this has a little squiggly here. It's called a point of inflection. So if you want to get that graph darker on your page, go for it. But you need these points, 1, 2, 3, 3, 5, 7. And then the yellow, I think you should know that as I'm reading this, my hand's going down. But the words describe the Y's. And this is what people screw up on this. You need to give me the X's that create these decreasing and increasing Y's. So that's the biggest mistake people make on this, and a very easy concept, but they jack it up because they give me the wrong thing. So this is already describing the Y. So look at my X and Y finger. As I'm out here, I'm up here. And then as I plug this one in, the Y goes down, Y goes down, Y goes down. And then Y goes down. And then after this, the Y start going up. So I need these X's that create these decreasing Y's from negative infinity to what? 1 or 2? 3, 2, 1, go. 1. So it's from negative infinity to 1 that this graph decreases. And then also from 5 or 7, 5 to, and then again, 5, 6, 7. The Y's decrease as I plug those X's in that order. So again, you got to name the X's. I guess you could put a union there. I don't think it really needs to be probably the word and, but it's the same thing. Then you get it. It's increasing from 1 to 5. All right, it's the X's from 1 to 5. This graph. This is just a point of inflection. It never changes direction. All right, so don't worry about that. All right, I'm not doing the next one. That's enough of that. And now we'll graph this one real quick, and we'll just talk about it. Again, if you don't know where the absolute value is, that's going to be rough. Okay, we're just doing this over and over again to get stragglers that don't pay attention. It drives the teacher crazy. They're the creators of their own demise. All right, so math, num. Not even going fast. There you go. And then if you have an old calculator, it just says ABS. X plus 1. This is what you're supposed to be doing in your homework with these questions that don't have a picture. Plus math, apps, num apps, sorry. Again, and then X minus 1. Can't say I'm going fast. Minus 3. I don't even know what I was looking at on this until I grabbed. I wouldn't even know how this would graph, but now I see it. Okay? And then look at that. What's the graph doing right there? Where does it end apparently? At what number? Not 0, negative 1. Okay? And then what's it doing right now? constant from -1 to 1. And then what's it do now? From 1 to infinity. Okay, I'm not writing that. Okay, x's. X's is what you name. Okay, all right. This is ugly. And I guess when I do 1, I'll clear it up even more. Number 6, relative extrema. Okay, and I'm going to skip 7, which is even odd. And then I think boundedness, and we'll be good because that's what I did last hour. So 6, I'm going to skip even and odd for tomorrow, and then 8, I'm going to do today, and then 9 I'll do tomorrow, which is end behavior because I missed with them. I just threw this old sketch here. They're on the board right now, you liars, if you say you've never seen this before. And then look in the backboard. See those polynomial functions? That is Math 3 regular right now. So a year ago, you looked at x to the thirds, fourths, and fifths and saw the waving functions. I just always have Math 3 students when they come into CAT. We never saw this. You're lying. You actually have. All right? So this is like a negative x to the fourth. That's why I put this over here. Power of 4. All right. Now, we will do this in chapter 2, and we'll do it faster than Math 3 because it's seen before, and add some things. But we're going to talk about this now about extrema. This is called a relative or local maximum because you might want to highlight it, maybe the relatives different than the absolute, because there is a higher y value here than there is here. So relatively speaking to this area, that's the maximum. Again, it's describing the y. I'll tell you how to name this when we get to the other one. These arrows go down forever. So this is a relative minimum relative to this position, but not the overall minimum y value. Then you look at that top pink point, that is absolutely the highest y value. So that's called an absolute minimum. I'm sorry, maximum. Sorry about that. All right, so that's what that says. Then cross off that even odd, and then maybe add this, right? Did I put this in yours, or did I add it later? So I'm just going to do, I'll just do this one. The other period, I did the other one. I only have time for one. So I'm going to go ahead and minimize this. And all it is what are the extrema? Name them. And then I'll do it, and I'll do it on the graphing calculator. So again, clear, a little bit easier one. X. Again, I'm emulating what you have to do tonight. You got to use a graphing calculator. If you don't have a graphing calculator, this is not going to go well. It's a prerequisite for this class. All right. Graph and then maximize. Pretty standard. That's what an x cubed normally looks like. I already did this. I did this when we had to get the range for that one question. Second, calculate. Let's do the maximum first because I'm closest to it. Maximum. And then I arrow over. Enter. And then I arrow to the right of that high point. Enter. Look at the arrows pointing at each other. And then press enter. And then you know what I'm going to do? I'm going to pull this to here. Hopefully it goes right there. Come on. I hate this program. There it is. It just put it. Okay, it did. It took a while. All right. Sorry, program. I didn't mean to yell at you. All right. I guess I can't move that. Here's what you got to say, though. And I'm going to put this down here. Listen. Again. Some of us, I don't know. The minimum is. This is how you word this. 4.079. I just kept going because I should have rounded to 4.08 and I just didn't want to erase. At x equals negative 1.155. I guess I'll go 3 decimal places because I did the other one. Usually 2 decimal places is fine. I don't have hard rules for that. But that's how you word that. The minimum is actually the y value. Where it's located is the x value. And that's what you got to say. Then the other one, because of time, I'll just find it, but I'm not going to write it. Second, calculate. This is now a minimum, 3. And I actually am left of that. So I could have stayed right where I was at. But I just decided to get a little closer. Don't go past. And then right bound, I need to go right. Enter. And then enter. And then that one's 1.15. Oh, that's interesting. And then negative 2.07 or 2.08. So you'd say the same thing. That's where that minimum. So I just showed you how to do it. That's really the point of the notes. All right. So again, it's up to you to get that done, get that taken care of. And then here's the last thing. Here's what you should do. Go to your front of your notes. See that space on the bottom? And maybe go underneath the left side and just put boundedness and number it number 8. Don't really care about this. It's actually not really a big deal. I could actually go through the notes, all the things that we graphed, and show you who's bounded above or below. But maybe write this word definition down right there, and then maybe scratch a couple pictures. You don't have to do them all. A function is bounded when the range is basically not going to positive or negative infinity. A real simplistic definition, which works. Just like my simplistic definition of what a function is. No repeating x's. Don't worry about all these long-winded definitions that I didn't understand when I was little or in high school. Fumble. Is that a fumble? All right. Okay. Should be done writing those words. This is a rational function. It appears to have boundaries here and there, but it's boundless, both going negative and positive. So this is not bounded at all. So there's no boundaries, no lower or upper limits. It's very simple. Then you have the second one, and again, you can write as many as you want, or just but it does give you an example of each. This does go forever up, but there is a low point. So this is said to be bounded below. I don't know. I've never really heard of this until this book. So I don't know. There he is. He always got a comment. All right, and then this one, there he is, a frowny face, has a boundary above. Now he's giving me dirty looks. Not hard. And then this last one, this is like a heart monitor. What? All right, still going. Beep, 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 beep. Right? So it's bounded both above and below. You could say that or just say it's bounded. Now, I could go through all the notes and talk about some other ones that are bounded above, below, or bounded totally. None of them are bounded totally. Could go back up to here, and I'll go back down to that as you're finishing up here. I can go back to, where did we have that exponential function? Where did it go? Didn't I graph an exponential somewhere? Here we go. That is bounded below. That is bounded below because there's a horizontal asymptote as a boundary, and it doesn't get any lower than that. Okay, and I can't think of anything else that I've seen here earlier. None of these are bounded because they went off. This actually is said to be bounded below because it doesn't go any lower than that y value of 5. So 18 there and that number 3 that I numbered over there are bounded below as well. All right. Then the last things that we'll do is even and odd. I'll sneak that in tomorrow. And then what I didn't get to was end behavior, which is just limits statements for what the ends look like, which won't take long. And then we'll synthesize everything. Okay. Finish that off. Stop sharing.